Hi, I'm Evan Lewis on the Evan eCent channel again, and I've made recent videos about understanding gear trains and another one about metric to imperial conversions and vice versa. And one of the viewers asked me to make a video about gearboxes. Now, the gearbox is actually quite simple to use, but I'll start by talking a little bit about how we copy the lead screw in order to make a thread and where the gear ratio comes into it. And then I'll go on to talk about the gearbox itself. And I've devised an elaborate method really to determine all the gear ratios in a gearbox so that the RideTheGearTrain program can use your gearbox. And in fact, it's all automated in the program. If you need to include your own gearbox and it's not already on the program, you can use the custom gearbox feature to enter all your own data, and it'll generate the code that's required for your gearbox. You can use it straight away, or you can send me the code and I'll insert it into the program so it's there permanently. So that's how it all works, and right at the very end of this video I'll show you how to actually do that. At the most basic level of screw cutting, we're simply copying the lead screw onto the piece of work we're cutting a thread on. So if there's a 1-to-1 ratio between the number of turns of the spindle and the number of turns of the lead screw, we get an exact copy of the lead screw pitch. So if the lead screw has 8 threads per inch, the thread we end up with is also going to have 8 threads per inch. We can modify that by introducing a gear ratio between the spindle and lead screw. So if we have a gear train, for example, that has a gear ratio of 0.5, we have the lead screw turning half as fast, and that makes a finer thread. And so the number of threads per inch is doubled and the pitch is halved. Now we have a gear ratio of 2-to-1, that's a gear ratio of 2. That means the lead screw is turning twice as fast relative to the work, or put another way, the tool is moving twice as fast along the bed, resulting in a coarser thread with a pitch that's double what it had been with a gear ratio of 2. It doubles the pitch, but the threads per inch is 1/2. One way to find out how to set up your lathe to cut a particular thread, particularly if it's an unusual thread, is to use my computer program, which I make available free of charge online, called RideTheGearTrain.com. So give that a try. One of the advantages is that you can enter your own set of gears, and it'll tell you which ones of those gears may be used to set up the gear train and gearbox to give the thread you want. In this case, we're cutting a 1.25mm metric thread on an Imperial lathe. And I've chosen to use the second line down where it says to use a 22 stud gear and then a pair of compound gears, 127 and 100 teeth, and then the lead screw gear is 56 and the gearbox setting is B1. Now if you click the draw button, it actually draws a scale drawing of the gear train so that you can see whether the gears are likely to fit together properly. It helps to prevent you from making any mistakes. And here we are setting up the gear train. This is the small 22 stud gear at the top with a screw in the middle. Here's the lead screw gear with 56 teeth. And here are the compound gears, 127 tooth gear connected to a 100 tooth gear. They're physically connected together so that when one turns, the other one turns as well. These are referred to as a compound pair. And this is how the lathe has been set up. So now we need to set up the gearbox for a setting of B1, so the left-hand lever goes to position B, and the right-hand lever gets moved to position number 1. And this should give you the gear ratio you need to produce that thread. It may not be 100% perfect, and it'll say on RideTheGearTrain what the amount of error is if you're not able to get a perfect thread. Often the errors are quite small though, and you can tolerate a small amount of error. Most bolts only have 5 threads on them, so there's not that much problem accommodating a little bit of variation. So how does the Norton gearbox produce all these gear ratios? What you see if you look at the underside of the gearbox, and if you're really keen and want to calculate all the gear ratios, you can look up the manual or take this apart and count the number of teeth on every gear and calculate all the ratios. But we've got a much easier method. This is the gearbox for an Imperial lathe, and the left-hand lever is marked with letters of the alphabet and right-hand lever with numbers. The right-hand part's much easier to understand because you see a whole cone-shaped structure of all the different sized gear wheels you can choose by moving the lever. The left-hand side is a little bit more complicated, but the gear ratio produced by the left-hand lever is multiplied by the gear ratio on the right-hand side because these two gearboxes are connected together in series. But I think that's all we need to say about the actual mechanics. We can calculate all the ratios from the label on the front of the gearbox. We'll start with the Boxford Imperial gearbox and go on to the Boxford metric gearbox, but actually this method will work for virtually any gearbox with a little bit of imagination. Now let's look at the gear ratios produced by the gearbox on my Boxford lathe. This lathe has a Norton gearbox, and these gearboxes are almost universal, or at least certainly found on a lot of lathes, but they don't necessarily have the same gear ratios. However, we can calculate the gear ratios, at least in relative terms, from the table that's provided here. This type of lathe, developed by Norton in 1886, has a lever on the left which has 5 positions in this case, 1, 2, 3, 4, 5, A, B, C, D, E, and these also appear in the table here, A, B, C, D, E. And there's also another lever on the right hand side which is numbered, so you can move the lever from position 1, 2, 3 all the way through to 8. And so that's how this table is made up. There is an extra line at the top here where they change the stud gear to 40-tooth gear, and I'll ignore that because I need to have all the thread calculations using exactly the same gear train. Okay, so how are we going to calculate what all these ratios are without taking the machine apart or looking in the manual? We know that this lathe has a lead screw with 8 threads per inch, so we start by looking at the gear arrangement for 8 threads per inch. That's on row A and position 1 on the number lever. So that's the gear setting you would use. We call this A1, A on the left-hand lever and 1 on the right-hand lever, and they'll give us 8 threads per inch. So what's so magical about 8 threads per inch? Well, we've just been talking about the fact that the thread cutting is a copy of the lead screw, and that we know the lead screw has 8 threads per inch, and when we set the gearbox to 8, we know that we must have an overall gear ratio of 1, so that the work is turning at the same speed as the lead screw. So that's our reference point for everything else we do on this table. To reproduce this whole table with numbers that gives the relative gear ratios of all the different locations, we could just multiply the rows by columns. For example, we could take this row here with 64, multiply it by its column 10, and you end up with 640 in this location, and all the numbers would be correct relative to each other, but you've lost the actual value of the threads per inch. Not really critical, but I've found it is better to take one more step, and that is to divide all the numbers in the first column by 8, which was the pitch of the lead screw. Actually, it's really the place where the row and column intersect, that number in there. We divide everything in that column by that number. So 8 divided by 8 is 1, 16 divided by 8 is 2, 32 divided by 8 is 4, 64 divided by 8 is 8, and 128 divided by 8 is 16. So you can see we still maintain the correct relative values of the rows, going in the order of 1, 2, 4, 8, 16, and many of you will notice that these are all multiples of 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. And the advantage of using this is that now if we use these values and multiply them by the columns, we now get the actual correct value of each item in the table. So 8 times 10 gives 80. I call this process of dividing by 8 normalization. All of this is done automatically by RideTheGearTrain, but this is how it works. Now that we've worked out the gear ratios of the gearbox, we need to find out what the correct gear train is to use with the gearbox. If you don't use the right gear train, of course, you're not going to get the right gear ratio. So there is a specific pattern of gears that has to be used in the gear train to get the correct results. And the table did say that we had to use a 22-tooth stud gear, but it did not mention the fact that we have to use a 56-tooth lead screw gear as well. I guess you have to read the manual. This is usually separated by an idler gear in between, but that doesn't affect the gear ratio. So it's like the 20-tooth gear is directly driving the 56-tooth gear, although in this setup we see that the 56-tooth gear is rotating in the opposite direction to the stud gear. And if we put the idler gear back in, we find that the direction of rotation is now correct. They're both rotating in the same direction. So that's the second advantage of the idler gear. It's mainly used to fill the gap and to correct the direction of rotation. So it's just as though we had a 20-tooth gear driving a 56-tooth gear. And this is the standard gear train, I call it. We have to call it something. This is the gear train that has to be used with the gearbox, and so I call it the standard gear train required by the gearbox. So the gear train ratio is 20/56, which is 1/2.8. When the gearbox is set to 8 threads branch, that is the A1 setting we were just looking at, and that's the same as the lead screw, we know the overall gear ratio must be 1, so that we're directly copying the lead screw. So the gearbox has a primary ratio of PR of 2.8. I call it PR, the primary ratio. Terms I had to make up myself. So the gear train ratio is 1/2.8, and it's multiplied by this primary ratio of 2.8 to give an overall gear ratio of 1. We know that's necessary. But this primary ratio applies to all the gears in the gearbox to maintain their relative values to each other. So all ratios in the gearbox must be multiplied by this primary ratio of 2.8. Now we go through exactly the same process for the metric gearbox. Notice that in Boxford lathes, the metric gearbox has the numbers on the left and the letters on the right. We start by eliminating the area where they use a 50-tooth stud gear and concentrate on the area where all the threads are done with a 20-tooth stud gear, just to be consistent. Next we find that the lead screw pitch is 3 millimeters, so that's our reference point. We look at the table and find that the 3 millimeter pitch is there on the table, and it corresponds with the letter lever being set on D and the number lever being set on 1. So it's a selection of D1 with a stud gear of 20, and it so happens that the lead screw gear has 45 teeth, although it's not shown on here. Now again we look for the place where the pitch is the same as the lead screw, which is 3, and select that row and also select that column. And those two, the row and column, define all the gear ratios we need in the whole table when they're multiplied together. As I did with the Imperial cable, I now normalize it by dividing everything in that selected column by the pitch of the lead screw, which was 3. So we end up with numbers of 1, and the next row down is a half, the next one a quarter, and next one an eighth. And they are similar to the series that we had in the Imperial lathe, but they're inverted. This is the standard gear train that you must use when you're using a Boxford metric lathe, and it's different from the gear train used for the Imperial lathe, and maybe different from many other lathes as well. So each lathe has its own unique standard gear train that you have to be aware of. There is an idler wheel in the middle, but it doesn't contribute to the gear ratio. This is what it looks like when it's running. And the gear train ratio, when you calculate it, is just 20/45, ignoring the idler. 20/45. Since the lead screw has a 3 millimeter pitch in the D1 position, it must result in an overall gear ratio of 1. Remember, we're copying the lead screw, which has a 3 millimeter pitch, to create a thread of 3 millimeters, and in that situation we need a 1-to-1 gear ratio between the spindle and lead screw. So the primary ratio of the gearbox must be 45/20, since the gear train is 20/45. So one must be the inverse of the other, so that all the numbers cancel out, and when we multiply the gear train ratio by the primary ratio of the gearbox, we end up with a ratio of 1, which is what we need to produce a 3 millimeter thread. So the primary ratio is 2.25. This gearbox shows that it has feed rates on here as well as threads per inch. So if you put the gearbox in position A1, you can either get 8 threads per inch, or you can get a feed rate of 0.0427 inches per turn. And while feed is just like thread cutting, the rates are much slower to give very fine cuts rather than a thread. You could use the lead screw as a form of power feed. A thread of 200 threads per inch has a pitch of 5/1000ths of an inch and could be used as a feed rate. However, we don't do that generally because it will wear out the lead screw in time. So instead, modern lathes usually have a separate shaft that provides the feed rate, although the Boxford uses a keyway along the main lead screw as a means of driving the power feed rather than having a separate shaft. Anyway, this tells us that the feed rate is 0.0427 when we have it set on A1. The pitch when you're in position A1 for 8 threads per inch, the pitch is 1/8 of an inch or 0.125 inches per turn. Now we have a value in the same units as our feed rate by inverting it. Also note on this chart here that it tells you about cross-slide feed rate. So these are the longitudinal feed rates on here. Let's make it a bit easier here. It says automatic cross-feed is 0.3 times the longitudinal feeds. So they've told us all the longitudinal feeds here, and if we want to know the cross-feed rate, they're 0.3 times these feed rates. So there's a gear differential between the two. The gear ratio for the longitudinal feed, or what I call carriage feed rate, is 0.0427 over 0.125 is 0.3416. But if you calculate this for several entries on the table, you'll find there's a bit of variation due to round-off errors, so I just round this to 0.34. And we just saw the label. It said that the cross-slide feed rate is 0.3 times that, so 0.34 times 0.3 is 0.102, which I round to 0.1. So those are the two gear ratios that we need to describe power feed. In RideTheGearTrain, that's one of the options, is to choose a power feed rate instead of a thread. Now that we've calculated the gear ratios for the gearbox, we can write down the equations that are needed to calculate the thread pitch for a metric thread. Now if we have a lathe with no gearbox, it's really quite simple. We just take the pitch of the lead screw and multiply it by the gear ratio to get the pitch, as we explained earlier. When we introduce a gearbox, we start with the same equation, lead screw times the gear train ratio, and now multiply it by the gear ratios provided by the gearbox, which is the F factor, which is what I call the number off the table, multiplied by the primary ratio that we talked about. And now we're in a position to actually calculate this primary ratio. So what we do is we take all the terms on the right-hand side that we don't want to have there and divide both sides of the equation by that same amount. So we can take the pitch on the left-hand side and divide it by these terms that we don't want, GTR, F factor, and lead screw, and that leaves just the primary ratio on the right-hand side. We flip the equation around to write this primary ratio equals to the pitch divided by GTR times F factor times lead screw pitch. To utilize this equation, we can take any thread that's on the copper plate on top of the gearbox or similar table, find any thread on it and apply its data here. Of course, we know the pitch of the thread we just chose. We also know the standard gear train ratio, which is to be applied here, since that's always used with the gearbox in standard settings. And we get the F factor off the table, which corresponds with that gear selector position. And if we've done the normalization process, this is actually equal to the pitch. And finally, we know the pitch of the lead screw, so we have all the variables we need to calculate the PR using this equation. Having told you how all that works, again I have to remind you that the RideTheGearTrain program does all this for you, so you don't actually have to know the equations. Now we'll switch to the Imperial lathe, which is really very similar. Of course, on the Imperial lathe we use threads per inch, which is really the inverse of pitch. So 1 divided by threads per inch is inches per thread, which is pitch in inches. So it's the inverse, and consequently we calculate threads per inch by taking the lead screw threads per inch and dividing by the gear train ratio, as we showed previously. And then if we have a gearbox, we add in the gearbox data, and the F factors in this case are actually in terms of threads per inch, so they don't have to be inverted. And so threads per inch is primary ratio times F factor multiplied by lead screw over GTR. Finally, we rearrange this equation to get the primary ratio, which is threads per inch of the thread we choose off the table, any thread, and multiplied by its standard gear train ratio, divide by the F factor, which again is usually equal to the TPI if we've normalized the table, and we include the lead screw in threads per inch, and with that calculation we can get the primary ratio and use that to do all of the above calculations. And again, that's all done for you by RideTheGearTrain. Now I'm going to show you how to set up a custom gearbox using RideTheGearTrain so that you don't have to do all the calculations we've been talking about, but you do have to put in the data pretty much as described. So we go to the main menu here and we'll scroll down past all the other data information, the lathe information, because we have our own lathe we need to put in. So we go down to item 10, custom gearbox, and click on that, and it starts asking some questions. It wants to know the type of lathe, whether it's metric or imperial, so we'll click imperial. And I'll use my Boxford lathe as an example, and it has a lead screw with 8 threads per inch. And I'll put it on automatic because most lathes will be able to use automatic, where you can use the change gears to make up any pair of compound gears. And it goes through and sets them up all automatically for you. Now we've got to copy the numbers from a row. Recall we looked at that copper table and saw these numbers going across the row. So it actually gives those as an example. I'll copy those and we'll go down here to the bottom of all those instructions. It's already in there actually, and we'll paste in this set of threads per inch across a row: 8, 9, 10, 11, 11.5, 12, 13 and 14. And then I want to know how those particular items are labelled, and then they're labelled 1 to 8. But you could actually change these to letters if you wanted to, like U, V, X, Y, Z, etc. Just 1 to 8. And now we look at a column. And again, remember that copper chart, how we drew a column on it. And the numbers went up: 8, 16, 32, 64, and 128. And they're labelled A, B, C, D, E. So this is asking for the labels for a row. Because actually these are labeling rows. Although they appear in a column, they're actually labeling the rows as we go down. That gets a little confusing. And next thing, it wants to know how many compound gears you generally use. This is not absolutely necessary, but it gives it a starting point for the program to set this to 1 compound gear as a default, but you can always change it to no compound gears or 2 compounds. And then we need to know what gears you have. Say we've got 20, 21, 24, 28, 56. And we need 2 56s if we wanted to have a 1-to-1 gear ratio, and need 2 gears the same. And then we'll say maybe 72 and 120, perhaps 100, just to say that we can do conversions to metric. And this decimal point here should be a comma, so correct that, they're all commas. Into the list of compound gears. Now, since we've done automatic, you don't actually have to have compound gears, but if you did have, you'd have something like 127/100. That's a pair that can't be separated, or you may have pairs that can be separated, like 63 and 80, which could be 2 gears that you can take apart, that are designed to work to spin freely as compound gears. So these are only used on certain lathes that aren't able to make compound gears out of the change gears. In other words, not automatic. If you put it on automatic, the program ignores this list. And then for power feed, the cross-slide power feed we decided was 0.1, and the power feed for the carriage was 0.34. And then we just want some general information about the lathe, and it's not critical, but this is for a Boxford Model A, and the year was 1955 for my one. And that's just going to be used to label the lathe. Standard stud gear. Remember we talked about a standard gear train? Well, a standard gear train has a stud gear of 20 and a lead screw gear of 56. And if you have a Chinese lathe, there may be some extra data you might have for the standard gear train. They sometimes have compound gears they use, but so that's just there in case they need it. And also on some lathes, particularly Chinese lathes, you may not be able to change the stud gear. And this is a pretty standard lathe, and it does allow you to change the stud gear, and the same for the lead screw gear. And again, these are just put in there to allow special cases. And then we come to final instructions. Just click perform calculations, and it comes up with a list of all the variables it's calculated. Primary ratio is 0.0446 in this case, and it shows you the numbers that have been assigned to the letter levers. Now remember, they went 8, 16, 32. Well, it's been normalized to 1, 2, 4, 8, and 16. So that's been done for you automatically. And then the numbered lever has the threads from one of the rows. And then it shows you a table of all the numbers multiplied together. So that gives the actual F factor, or the number that appears on the table. In the A1 position, it's 8, as you've seen from the previous table. Then it goes all the way down to an F factor of 224, which is actually threads per inch. Because we've normalized it, that's worked. The F factor has worked out to be the same as threads per inch. And this is our list of change gears, rather a long one, with 12 items on it, and our list of compound gears. So the custom gearbox has been set up, and this tells the programmer what to enter. So if you send me this URL, I can reproduce this printout, and I just have to copy this printout and paste it into the program, and it's ready to go. So I don't actually have to write the code. The code's already been generated by the program. So this is the code for the list where you specify all the details for each particular lathe and the setup. This is the part that goes in the choose lathe list, so it'll appear on the list. And finally, we've got some HTML which is pasted into the help file. So when you click the help button, you've got some information. And it's just put in a little bit of it, basic information that the program knows about this lathe. And that's it, you're finished. You can go to the main menu, and when you go to enter a new lathe, you'll find it's already got custom Boxford Model A 1955 Imperial as the name of the lathe. It's already been all set up and you can use it. Or you can send me the URL and I'll put it in there permanently. So that once it's in there permanently, you can go to this master list and scroll down until you find your lathe. So that's what it's all about. And that's it, we're finished. In case you don't know what I mean by copying the URL, this is the URL or website address at the top of your browser, and you can select the whole thing, press Command C on a Mac or Control C on a PC, and you can copy the whole thing. You can then go to your mail program here, message, and put the address in there. New custom gearbox, and tell me what you want to do, and just put in Command V in there, and it puts the whole address in there, and I'll receive that, and it contains all the data. Now, unfortunately, the email program has converted that so that you can't actually see what's in it. Let's open a text file, and you can see this is actually what one of these URLs actually looks like, and it contains all of those data that you've entered embedded in the URL. And that's why when I receive it, I can actually extract all those variables, and automatically they'll load into the program, and I'll be able to insert your lathe for you.